All right, moving right along to our next talk by Megan Kreiger. Megan is a mechanical engineer at the U.S. Army Engineer Research and Development Center. She's a pioneer of the field of additive construction, and she took a new approach to modernizing of construction through the scalability of 3D printing. Megan led the development of large-scale deployable construction 3D printers that print on varied terrain, promote mobility, ease of build, flexibility of materials, faster construction, designed to be rugged and printed out in the open using conventional construction materials and reinforcement. Ms. Kreiger led the demonstrations of printing full-scale buildings, a bridge, and infrastructure components, most of which are the first in the Americas, if not the world. Megan Kreiger is internationally recognized as 2020 BuiltWorks Maverick, 2018 ENR Top 25 Newsmaker, 2018 USA CE Innovation Awardee, and in news around the world. She earned her Bachelor's of Science in Mathematics in 2009 and MS in Material Science and Engineering from Michigan Tech University in 2012. And with that, I will leave it to you, Megan.
Okay, let's see here. All right, sharing screen. Is it gonna work? Can you guys hear me? Okay, so I'm Megan Kreiger. I am the program manager for the Additive Construction program at the U.S. Army Engineer Research and Development Center, Construction Engineering Research Lab. And basically what we do is we do construction scale 3D printing. Specifically, our main focus area is concrete, but we also have other areas as well. So you guys have heard a lot today about 3D printing, and many of you are well aware of all of the things that exist currently in the 3D printing realm. Now, what I do is a little bit different, right? We're talking about 3D printers that are larger than a building, and that a lot of the things on the small scale just don't really apply real well as we go up. So before I really get into the technology development we've done, 3D printing, I've been in this realm since about 2011. 3D printing has been a realm that has a lot of hype associated with it. Back in the early days, the hype was extremely intense, and more recently, the hype has kind of died down a little bit. But 3D printing in general has been known to hype up a lot of aspects associated with, what its use cases are, how it can apply to the real world, as well as really what it can do. So 3D printing used to be the solution for everything. Like, we were going to take over the manufacturing industry. We were going to be able to replace everything in the existing manufacturing world, right? We know that that isn't reality. We know that additive manufacturing has its use cases that are that intertwine with conventional manufacturing processes. Like, there are areas where you would use a conventional manufacturing process that will far outbeat what an additive manufacturing process could do, as well as the opposite, right? We want to intertwine technologies to use them for the ones that apply most to their use case. So this is called the Gartner's hype curve. Gartner makes what's called this expectations versus time plot for various levels of technology, not just 3D printing, but just across the board. And the reason why I'm showing you this is to kind of give you guys an idea of where these technologies fit in the realm of development, as well as where they can go in the future. So as you look at this, you start out with what's called an innovation trigger. So a technology is developed and people get very excited about it. And as you start telling people more and more about what your technology can do, people start believing that you can do those future concepts. So as you keep going up and up on that peak of inflated expectations, you get to the point where people realize that you cannot do those future concepts today, and that maybe that isn't the best use case. And so as you keep selling your technology, at that higher level concept, what happens is you start to go through the trough of disillusionment, which essentially means that people have lost faith that your technology applies to their applications because you've been overselling it. And then after a technology has been around for a certain amount of time, it goes through the slope of enlightenment, which basically is where a technology is recognized for its certain applications. Now, after it makes it through that phase, once it's accepted in the technology realm, it is known to go into the plateau of productivity. So this would be things like on this plot, which is specific to 3D printing from 2018, things like the 3D printing service bureaus. You can go online, you can buy 3D printed parts from a number of different websites and be able to just have them in your house with no worries. Now, as you go through, what will happen is when you look at these technologies, there are certain things on this plot, right? From all the way from nanoscale 3D printing, 4D printing, and beyond. So things like 3D printing service bureaus, hearing aids, things like that are very well accepted in the industry and have made it kind of past that danger point. Now, what happens though in that dip, in this curve, the trough of disillusionment, that's where technologies go to die. Now, when we talk about what I do, construction scale 3D printing, I like to call us macro 3D printing, right? We're pretty macro, buildings pretty macro. So I figure we kind of fit into there. Now, as time has gone on, 2019, 2020, I think we're just past the peak. But as far as discussions for how many people think that 3D printing, concrete, and construction is overhyped, I think that my question on that is, how many of you have seen a video about someone 3D printing a building? And how many times has that building, been quoted to say, much like the early 3D printing days, saying things like, we can build a house for $4,000. We can build a house under $10,000. We can build this in 24 hours. You can buy a 3D printed house. What you have to realize is that we're going through that peak of very overinflated expectations, and that a lot of those aren't realistic. And so how do we get through that as we go through this technology process? I am a very honest person when it comes to technology, and I will tell you the truth about anything. And part of that is because I want the technology to succeed in the applications that it fits in most. And so while I'm developing these large-scale technologies, really what I want to look at is this meeting the need of the person who's going to use it? So what we do is we work on collaborating. So we work with academia, we work with other government agencies, we also work with private sector, we work with International Building Code, American Concrete Institute, a number of different people, all the way from the materials side through the end use and testing and validation side. Because this is how you avoid that trough. Because if the technology goes through that overhyped part, it potentially could die, even though it could be superior to other methods of construction. So we're trying to avoid what's known as the ego void in a technology development, where we want to recognize that we sell this for its own personal use, not for what we think it could do 10 years from now. And so what I want you to do is go through this little exercise with me. I want you to picture yourself, okay, in your mind with your goal to create a wall, right? And this isn't a manufacturing setting, but say you're out in the field with very limited supplies and equipment. And the only things at your disposal are really some wood and some basic woodworking equipment, or metal and some basic metal shop and welder, right? So this is getting into, why do we 3D print buildings? Okay, why do we 3D print infrastructure? So when we start out, you look at the picture on the left, it's just a basic, rectangular wall section. Now picture yourself how you would make the formwork, that wood form or that metal form of that wall section. That's pretty easy, right? Even if you have no experience in concrete, no experience really with woodworking, you could probably figure out how to make a rectangular structure with wood or metal. But as we get inherently more complex, you have to start to think, okay, that next image is a hollow rectangular wall section. Now, even if you aren't familiar with these methods, you might be able to figure out, okay, I can build a piece of formwork inside that I can remove afterwards. How easy is it to remove a piece of formwork from the inside of an object, though? And then as you get more and more complicated, when you start adding different pockets for reinforcement, or you start adding different cells in these structures in order to add things like insulation or different materials for different properties, how would you make the formwork for those inherently more complex structures? Once you get to the far right picture, that one, removing that inner formwork is very difficult. You can use something like foam and make sure to remove that using acids and such to get it out. But if you ask someone to make a form for that, they probably wouldn't like you very much. Now, let's get into the real world, right? Is when you go into construction, architects love to design, and they've always been limited by the current conventional practices. And so when you look at this picture and this image, this is a wall section that, as you go up in the Z direction, changes in the XY. Essentially, it goes from a zigzag structure at the bottom all the way to a straight-walled structure at the top so that it can integrate with the roof line. There's many reasons for this, and we'll get into that later. But picture yourself making that left wall. That's a solid wall. You know, you might be able to figure out how to make that shape. And the thing that you can't see is on the backside of that wall, it's that same shape going in. And so, like I said, it goes to a straight wall at the top, but there's a complex geometry on the backside as well. Then you go to a hollow wall section. If you ask someone to make this form, they would just say no. They would tell you it's far too expensive in order to make. And then as you get bigger and bigger and you expand this wall section into an actual full-scale house, you need to understand that all of these components, even if you 3D printed the formwork, or even if you CNC'd the molds to make these objects, all of those things have a limited lifetime and can only be used for, depending on who you talk to, wood forms can only be used for like 3 to 5 times if you're lucky in these kind of environments. And metal forms, they tend to only last maybe a dozen. And even before that, you need kind of a welder to come in and fix them. And so what can we do with 3D printing, right? So 3D printing allows us the ability to make these complicated structures with very little added cost, if any. So now our research group's priorities are to basically test the capability to print different kinds of custom designed expeditionary structures on demand in the field using locally available materials. And that's any kind of infrastructure, all the way from buildings to bridges and other objects. Now, the reason why I do it is for the military, right? Is that we want to make it easier to do construction in the field, have less logistics associated with that construction, as well as reduce the cost and the working and the risk for the working environment for our soldiers. We have gone from developing in-house printers all the way up through doing full-scale structures. And like I mentioned, with this kind of construction, you can reduce that cost based on the complex geometries, and even for those simple straight-walled structures that I showed you in the beginning. Probably doing a solid wall is not going to be great, but all of those other walls, you can get a reduction in cost simply because you are reducing the labor associated with making that wall. All of those formwork, the concrete formwork that you guys pictured in your heads, how long do you think it would take you to make those? If it would take you a couple hours to do, well, we can 3D print 8 of those wall sections in about 8 hours. So can you make, 8 forms that you can cast and put in place and do all that in that same amount of time? So even just the time is a savings alone. And because we're reducing that time, there is a direct correlation to reduction in cost. And not only that, but with our complex geometries, we can increase the strength of the walls and add different capabilities and different applications for that. So one of the other aspects associated with this is the energy performance. And we'll get into that more later, but because you can change the internal cavity of your wall, you know, it doesn't have to be solid, doesn't have to be hollow. It doesn't even need a zigzag infill. We can put pockets of all different shapes and geometries and sizes in order to make sure that it can meet the application that it's suited for. So the real big benefit of this is the reduction in hard labor. So instead of soldiers going out there, building form work, doing all these things that many injuries can be related to, now we're talking about just doing normal concrete work and then controlling everything with a computer. So even if it uses the same amount of people, it still reduces the hard labor. And then we try to do it with about 4 people instead of 8 for typical construction. So additive construction is a little different than the rest of the 3D printing realms you've seen. We not only have to deal with the things like software and equipment that you guys do and the materials development and testing, but we also have to deal with things like structural design and architecture and being able to integrate that with the end users. For us, that's the military. And so in this process, we've had to develop everything from the ground up, as well as work with our partners in order to develop extra capabilities in order to meet all these needs. Because when you talk about large-scale 3D printing, you can't just use the precision rods and bearings and all the things that we typically associate with small-scale 3D printing, because cost becomes an issue. When we're talking about printing outside in the field, see that picture next to equipment? We're talking about outside, leaving a printer in all weather conditions while we're printing infrastructure. So that equipment needs to be able to handle rain, snow, cold weather conditions across the board in order to be able to withstand the environment. And so these kind of extreme conditions for this kind of equipment really sets the bar for everything else. So we have done many different applications, whether it's full-scale buildings, 512 square foot. We've done a couple of those, as well as we did the first 3D printed bridge in the Americas. But really our focus is not on those kind of demonstrations. It's really on expanding the technology to be used by the end user and to make that stage of tech transition. So we use industry accepted concrete materials, including cement, sands, additives, reinforcement. We use rebar. We try to just integrate existing materials and codes into this new technology so that all we're changing is the method that the concrete is placed. Because when we talk about that, the Gartner's hype curve, we want to make sure that we are collaborating with and we are developing a technology that meets its end application. So the different kind of construction methods you can really go into are things like print and place. So this is what we really focus on. It's where you take a design and you print it where it's going to live. Like, you don't move that. So you can print an entire building in its spot. That's what we did for both of the structures that we did. And you can also integrate that with components. So what you can do is you can pre-print components through 3D printing offsite and then put them in place. So you can pre-print objects much like a precast plant would create conventional objects and then put it into place either in a printed structure or another structure as well. Typically, we use preprint to do smaller things. So things like road construction barriers. We would preprint that, move it into place. And really where the benefit is for the military is instead of transporting that from several countries away wherever we're going, we can now just print that in the same country near site to where we are. And that saves on a lot, and especially since we're using conventional concrete materials, the logistics burden is very low compared to typical construction methods. In this process, you're not limited to just 3D printing. You can use traditional formwork. You can also print the formwork. You can print the walls, and then you can put on a conventional roof. You can print the walls. You can put on a concrete roof. You can even print the concrete roof itself, but there's a little bit more liability associated with printing a roof as opposed to printing the walls of a structure. And when you look at the structures that we did, they are fully reinforced structural buildings. The energy performance of these structures as well. When we start looking at how can 3D printing concrete, you might think concrete, that's going to be a cold building. Well, not if you can reduce the thermal bridges within the envelope in order to create a structure that is enhanced for performance. So all of these structures, you can finish them out however you want, just like regular construction. But when you talk about that interior part of the wall that you see here, you can get different properties associated with 3D printed buildings than you can with conventional. So at that top picture there on the left, that one is a conventional like CMU block wall. That has, you can see from that image there that it has terrible thermal bridging, right? Unless you put in insulation on the exterior or on the interior, depending on your climate zone. But really, when we talk about the 3D printed aspect of this, we can get similar or better R value to CMU. And that similar is without any changes to what we do. So as we go through, you can apply all these different things to make these buildings superior to existing construction. And the big thing that people always ask me is cost. And so I like to show this slide because people have been told, the wall that you can print a house for $10,000. In reality, you can print the walls for pretty low cost. You can see there for just the wall costs of a typical structure, your wall cost is going to be about $6,000 to $9,000, depending on the type of construction method, whether it's conventional or 3D printed. You can see that that's already over what the cost estimates that people give you are. And the reason why is that they are giving you future concept ideas. But a building is not just the printed walls, right? The building is everything inside of it. All of the insulation, everything associated with the building, the reinforcement, the bathrooms, the piping, the electrical, everything to finish out a building. So those kind of estimates people give you are just unrealistic. What we've shown with cost is that we can reduce the cost of conventional construction, mostly due to the amount of labor associated with formwork construction for cast in place concrete on the right. That's the orange. Because we don't have that formwork labor, now you can reduce the cost based on that conventional concrete method. For CMU block, you can reduce that cost because of the placement labor for those CMU blocks. Because most buildings take about, even in the field for the military, take about 2 to 3 days at minimum to construct. And that's for a very basic structure with no real amenities at all. With 3D printing, we can print a structure within 48 hours. And depending on the size of the structure, you can get those down to those kind of 24-hour limitations as well. So I want you to think about 3D printing, right? What can we do with 3D printing for a building? This is a building on our facility that we printed. And this is that design I showed you in the beginning, that wall that morphs in all directions as you go up to make a flat surface at the top. We printed wall sections to test this before we printed that full-size structure and did structural testing. And when we did this testing, it showed that these walls are 2.5 times stronger than a conventional straight-walled structure of 3D printed material. So just changing the geometry with only a 10% increase in material to make that slowing topology. We printed this building in about 48 hours. And we were able to do it with personnel that had never used the equipment before. We trained them on how to do it and they just printed it. And the real story related to that formwork that I need to tell you is that all of these roof panels on this building are cast. And when the Marines came out to build this and they build forms for a living, they told us that these roof panels could potentially be done in about 3 days for just the formwork. The formwork alone, just for the roof, it took over 4 weeks to get done with grouting and reinforcing and everything. So the roof took over a month to do. The building was printed in 48 hours for the walls. So I want you to think about that is when we talk about complicated formwork like those roof panels, because those roof panels have built-in beams with them and they slope as a roof does. When we talk about complicated formwork, we're not talking about days to build a structure for formwork. We're talking about months. So now we can take things that would normally take months and are cost prohibitive and make them completely reasonable for the general industry. Another case, the last case study I want to show you guys is this bridge that we did. This is an example of that kind of pre-print plan. We printed 3 different bridge beams for this, as well as 2 piers for this bridge. And the intent of this was to just show the concept of printing a bridge. From the time that we printed that last building I showed you to the time that we printed this structure, it was about 3 months notice. So they said, can we print a bridge? We said, sure. And then 3 months later, we had finished this. That included traveling from our location in Champaign, Illinois, all the way down to Camp Pendleton, selecting materials to print with in Camp Pendleton, California, and being able to print with it and train all of the uniformed personnel you see there on how to print with this technology. This bridge was actually printed and put in place within 6 days of starting. And most of those elements that you see there are only a couple days old. And when we did this, we tested it, right? Because we want to show the end application. For the military, we're quick and dirty as far as trying to get this job done. We're not concerned about a lot of precision. We're concerned about performance for the short term. And so when we tested this, we expected to get a load of around 15,000 pounds. We actually got about 45,000 pounds, which means these structures can be even stronger because instead of breaking as a single kind of concrete structure where you have a crack that goes down, we can now visualize this more like breaking like wood. And so with this, we can get increased loads on these types of structures and increase the speed of its implementation. And so as we go forward, you know, I could show you lots and lots of images of beautiful buildings of what people have done, but there's a new building coming out every day. There's a new different design. And really what I wanted to show you here today is why we do what we do and why the industry is moving in this direction. It's not just about printing houses less than $10,000. It's about improving construction across the board, where construction is usually considered the field that is reluctant to change, and bringing modernization to the construction field in ways that are from 3D printing and beyond. And with that, I will end my presentation. Do you guys have any questions?
Yes, they do. Such a great presentation. I think we have time for maybe just one, and I think this is a burning question. How do you deal with building codes and regulations?
So we have a number of people on the team that are associated with American Concrete Institute and the International Building Code, and we are developing methods for testing and evaluation and directly contributing to code development such that these structures can be approved in the field. Typically, when you see these buildings out in normal like houses and such, they're built under exceptions in the building code where they have to test like 1 or 2 components in order to show that it's structural. We're trying to move it beyond that so that we can start proving out 3D printed concrete in general. And we work with other materials too. This is just our primary focus, the one that gets the most attention.
Awesome. Well, thank you so much, Megan. This is a great presentation. Thanks so much.
Thank you. And if you have any questions, my email address is right there. Feel free to reach out, as well as I'll be available in chat and sticking around for a little while to answer any questions you guys might have.
All right, thanks. We're going to step down for a second and then pull our next speaker up.
Thank you.
Thanks.